I bet I couldn't do that again if I tried. Dad, you want to get that on video? Why should y'all have that?
I don't know.
Okay, so we can use technology here. So we're just, remember what we're trying to do, let's kind of wrap up a couple questions on mean value theorem. So the whole idea on the mean value theorem for integrals is if we want to establish what the average value of a function is on an interval, it's always equal to the area under the curve divided by the width of the interval, right? That's how we do it. And then if we want to, so we're going to answer several kinds of questions in a calculus class about this. We're going to want to know what is the average value, and then we want to know where does the function equal its average value, which is just an algebra, like 2, pre-calc kind of question, right? It's not really a calculus question. So this is the one we left off on yesterday. Right? If we want to know what's the average value of the function f of x equals sine x on the interval from 0 to pi, well, we just have to, the average value is going to be the area under the curve divided by the width of the interval, which is just pi. Right? 0 to pi is the width of pi. Okay? So the antiderivative of sine is minus cosine, and then we just have to evaluate that from 0 to pi. So we get minus cosine of pi minus cosine of 0. Cosine of pi is -1, cosine of 0 is 1. And so if we simplify this, what do we get? We get -1 times -2 is 2 over pi, right? So the area, the average value of the function is 2 over pi, right? Then all we have, so that's the answer to the first part. If we want to answer the question, where does the function equal its average value? Well, we just take the original function, which is sine x, right? There it is. And we're going to ask the math gods, where does sine x equal 2 over pi, right? And we just solve that equation. Now, that's not going to be at a convenient place. That's one that we would solve using technology. Or we would just, we could, for example, if we're using Desmos, which is what probably you'll be using. Remember our trick for solving an equation in Desmos, great trick. All we do is we're just going to graph the left side of the equation. Make sure we're in radians mode, which we are. We're going to graph the right side. And on our interval from 0 to pi, not our interval, I think it was 0 to pi. So on our interval, I'm just going to go to the graph and I'm going to change my domain. So the window, I'm only going to let it show from 0 to pi. And if I do that, I can see that I only get 2 places where that happens, right there and right there. My functions intersect. So those are my answers. Okay. I'll take a picture of that. How about? Okay. All right. So then let's just do this whole problem up with technology, right? If I want to find the average value of f of x equals 2 secant squared x on this interval, what would I do in Desmos? Right, so mean value theorem says average value is just what? What's the average value of a function on an interval? What is that? What's the average? How do I calculate average value from A to B?
Area under the curve minus the
Okay, area under the curve. Well, here's my curve, 2 secant squared x. So in Desmos, I can just pull up the integral function. It's under miscellaneous. There it is. So the integral from negative pi fourths up to pi fourth. Whoops. That's not what I wanted. To pi fourths. There's my limits of integration. And I'm integrating whoops. Darn it. I gotta hit the right arrow. There we go. To secant squared x dx, and then I want to just divide the whole thing, so I'll highlight it and divide by pi fourths minus negative pi fourths. Right? It's all in I mean, as long as I know how to set it up, I'll let the technology do it, and that's my answer right there. Okay? And I don't, say it again?
If we wanted to find out if it was actually just pi, we just divide that one answer by pi, it doesn't cost.
Right. So we could, if we wanted to figure out what that is in terms of pi, we could do that. We could just take this whole thing, and I hope that maybe that's enough decimal places. We'll see. That's kind of a good trick. If I divide, whoops. Hope it's not doing that. I wonder if I have to, there we go. Oh, it's trying. But it doesn't really it doesn't really work. It's not enough decimal places. So that's a good trick, but it doesn't work. So we'd have to be content to just take that as a decimal, which in these kinds of questions, like the ones I gave you, I let you just round it as a decimal. I think I had you round it to 2 places or something. Okay. So it'd just be 2.55 rounded to 2 places. Okay. That's how you do calculus in an engineering job. You're doing it using technology, but you got to know enough calculus to know how to set it up. Oops, let me take a picture of that. How about?
Are you by chance recording this?
I am recording this.
I was just recording.
You're famous. Okay, so what about something like this guy? Now, I think I have this one. Okay. Yeah. Okay, so here's our function. We want to find the area under the piecewise function. Let's just use technology again. Okay, so this is, there's 2 parts to this piecewise function, right? We've got x squared when x is less than or equal to 3, and we've got 18 minus 3x when x is greater than 3. Oh, serious? Who's it going to? I mean, what I have. There you go. Yep. Okay, so there is a way, and I haven't figured out how to do it yet. There is a way in Desmos to actually write a piecewise function. I've done it before, but I can't remember exactly what that is. But really, all we need to do here, if we're trying to add up the area under this curve, and I think it wants specifically in quadrant 1, well then that's just going to be this area in there. It's kind of like, it looks like sort of like a tweaked little triangle, right? So how am I going to do that? This really isn't a mean value theorem problem. What am I going to do?
You go part way and then with one function, then you go down.
Okay. Good. So if I know, I just need to figure out where the functions intersect, and we could do this algebraically, but I'm going to save a little time here. I'm sure you're okay with that. So they intersect at x equals 3, right? And so from 0 to 3, I'm just going to add up the area underneath the red curve, right? And then from 3 up until it looks like 6, I'm going to add up the area under the green curve, right? So that just looks like, if I do all that stuff, I got this all drawn up here. So there's the area under the red curve, right? Okay, that works out to be 9. Okay. Here's the area under the green curve, and if I do that math, that works out to be 13.5, and so I just add those up, and that's the total area, right? The moral of the story being, I've got two different functions that define the top of the area function, right? And so I've got to do two separate integrals. Say it again.
How do you keep the area?
Well, I mean, I did it using technology, but all we would have had to have done, this is a pretty easy one to do. I would just take the integral of x squared from 0 to 3, right? And that's, if I do that, if I take the integral of x squared from 0 to 3, Desmos tells me, like, I just picked a to be 0 and b to be 3 in Desmos. And f of x is what we defined as x squared, right?
How did you set it up in the shaded part?
How did I set it up? Oh, the shaded part?
Yeah.
Oh, it's just a little technical wizardry here. You just set it up. What I'll do, if you guys want to mess around with these, and I know I keep saying this, but I promise I will. I'll put links to, I can publish all these as websites, and so I can give you links to these. And if you want to save them, what I would do if I were you, honestly, before you go to college, get a Desmos account. Like I just linked to it through my Google, and I'll put all this stuff up there, and you can just go to it, and then you can copy a version for your own and just keep
Save
it.
a new function to it?
Yeah, and just save it as something under your account, and then you'll have them all for later. And there's just a way. This is, I'm probably not going to take the time right now to go through and show you how to do it, but you could, if you looked at it for a second, you could figure out what I did there. And there's a million. Most of the time, if I need to figure something out on Desmos, I just Google it, like how to, like this. I think this one was visualizing area under curves. Desmos is what I Googled, and it gave me stuff that it's easy to just tweak and for your own different examples. But it works pretty well. And then a lot of times in Desmos, you can do these cool little, like you can set up, and this is something, as we get further along, I'll show you some more examples with this. But what's really convenient to do in Desmos is you always define whatever the function is you're working with, call it f of x. And then you can go down and you can end up doing the integral in terms of f of x. And you can go change that function if you want to and just reuse the same template. And then you can, these are called sliders. You can set up a slider for the upper limit and the lower limit of integration. And you can either go in and just drag the slider, and look what happens to the graph if I drag the slider. It's pretty cool. Like if I drag the slider, see what it does? It's changing the area under the curve, and it changes the answer also. Okay. You can also, with the sliders, you can just go in, and if I want to do something like some specific value, I can just type it in too. Okay. Very useful. Okay. So I should take a picture of that, I suppose. Okay, so if I wanted to do one like this, like an area contained by some functions then, thank you, sir. If I wanted to do an area contained by some functions, I can do bounded area example, is that one. Okay, this is pretty straightforward and simple. So all I did here is I just set up those three functions. I guess I haven't really done the whole thing yet, but if I want to find the area bounded by all three of those, what would I do? You guys tell me. I'm not going to make it real fancy where you can see the area, but if I want to find, this is the area I'm looking for right there, isn't it? Right, it's that area. So what could you do? And this is kind of an important calculus question. How would I find an area, a bounded area like that?
The area between where and where.
Between, so it's going to be the interval over which we're finding the area is going to be x goes from what to what. Okay, does that make sense? I'm going from 0 up to pi over 3, right? That's the width of the interval. Yes, Kirk, what do you think?
So if you just find the area from 0 to pi over 3 under the red one and subtract the one from the other one?
Bingo. That's what you do. This is called area by subtraction, right? We do this a lot in calculus. So if I want to find an area that's not bounded on the bottom by the x-axis, I've got a ceiling function and a floor function, what we call it. And I'm just going to take the complete area under the ceiling function and subtract the area under that floor function. And then that's going to leave me the part in between, right? So we can, once again, we could do this on Desmos. You know, we'll make short work of this. So I want to set up an integral of the top function. And I'm going from 0, you said, up to pi thirds. And then I'm going to do the top function, which is just this. I'll just grab it there. That guy minus, sure. Right. Did that get better?
Yeah.
There you go.
Thank you.
You bet. So I've got the top function minus the bottom function, right? And then I just have to put a dx at the end. There it is. How about that?
Why is it like?
Isn't it the other way around?
Oh, did I do it backwards? Oh, I did. I did it backwards. Yep. You're right. So you can see why? How come it was negative then? Because I was adding the area up from top to bottom then, wasn't I? Right? There, this should be better. There we go. Okay? Make sense? Okay, once again, you guys can see that. Got the red function, area under the red function minus the area under the orange function. Okay? Now we could do all that fancy calculus, but in the interest of time, I'll leave it to Mr. Desmos. Okay, so here's another interesting question. So the calculus is not hard on this one. The integrals are going to be really easy to do. You'll get some practice on those, and that stuff is very mechanical. It's just like taking derivatives. But how do we set this up? Now they're asking for something a little bit different here. They would say use technology to find the total area. Now the area that we've always been finding, you could classify as net area, right? Like for example, we found the area, we looked at one the other day if we looked at a sine function, I don't know if we looked at this one or not, but if we didn't, this is a good one. If we look at a sine graph from 0 to 2 pi, what's going to be the area under a sine graph from 0 to 2 pi? It's going to be 0, right? Because I'm going to have exactly as much positive area as I have negative area, and they'll add to 0, right? So the net area is 0, okay? What do you suppose they mean, though, when they ask for total area? Yeah, we take all area, we're going to take all areas being positive, above and below the x-axis, okay? So what would our strategy be, do you suppose, for doing this?
2 times the area is half equal.
Okay, I mean, in this case, sure, because we have some symmetry, but just in general, let's assume we're not, like the function we're talking about here is not symmetrical.
We solve it for 0, and then we use that as one points in one interval. We go from that interval, and we go on the next one and add them up.
Okay, so we're going to have to add it up. So let me distill that down, because there's one other point I want to make about this. So we got to add it up in 2 separate pieces, don't we? We've got to add up this area and this area separately, right? But we have to be careful where we break the 2 intervals up, because what if I broke the interval up, let's say we went from there to there, and then from there to there. What's the problem?
Some of it will be lost.
Okay, when I add up this little bit right here, I'm going to get some positive and negative cancellation, and I'll lose some from my total area, right? So we have to be careful. Oops, not what I want to do. We have to be careful to pick the boundaries of our intervals. They have to be at the zeros of the functions, right? So we find those by just setting the function equal to 0 and solving, right? So like for this guy up here, we can do this. If we set this function
X plus 3 and x minus 1.
equal to 0, that's simple quadratic, right? We can solve this by factoring. X plus 3 times x minus 1, so we get x equals negative 3, 4, x equals 1. Those are the zeros of the function. Now, if I were to graph this thing, we could figure out, we can make a little sketch of this pretty easily.
Wouldn't we just disregard negative 3 because it's not
We would. So those are my zeros, right? And then, is this parabola going to open up or down?
Well, we can just take the second row and do that and find out.
We could, but we can even see that because A is positive, it's opening up, right? So we know that this one's going to look like that, right? Okay. So we're adding up the area on the interval from -2 to 2. So we're going to go from here up to there, right? So we can see that we're going to get some area that's below the x-axis, and we're going to get some area that's above the x-axis, right? Like that. Okay. In Desmos, looks like this.
So would we exclusively use technology for that, or could we calculate that by hand?
You could do this by hand pretty easily, right? There's going to be our positive, or there's our, that's the wrong one. Oh, I wonder if I screwed this up. I think I did. Oh, I did. Oh, man. I think I messed this up. I think I saved over the top of my total area example, ruining it. That happens a lot to me.
I didn't send any of those pictures.
That happens a lot to me in Desmos. You gotta be really careful how you save these things, because I've done this many times where I've done a bunch of hard work and then I've saved over it and lost it. Once again, all right. Well, we don't need it. That's all right. So, be careful with Desmos. Pick good names when you save things, and you'll notice that when you save graphs in Desmos, it always says you want to duplicate the graph. So if you check that box, it'll like save it as a new file. But if you forget to do that, like I did, that's what happens. You lose your file. Okay. So then we want to set this up as 2 separate integrals, right? The limits of integration for the first one are going to go from, they're going to go from -2 up to the end of that first lobe of the function, to the 0 of the function, which is at 1. Okay. So we're gonna get the integral of my function, which is x squared plus 2x minus 3 from -2 to 1, right? Plus the integral of x squared plus 2x minus 3 dx from 1 to 2. Okay, but if I do this integral, I'm going to get a negative answer, right?
Why are you so mean?
I'm pretty mean.
Why are you always picking on these kids?
I don't know. It's a good
Kids
question.
are
They're
right.
asking the same question right
I
about now.
know. It's so rough.
It is. So I'm going to get a negative answer if I do this one because the area is under the curve. How do I ensure that it's positive? Absolute value. Yeah. Right. So all I've got to do is I've just got to encapsulate the whole thing with absolute value bars. So I'm going to take this, take that integral, put absolute value bars around the whole thing. Whatever answer I get, I'll make it positive that way. Now I happen to know in this case, because I graphed it, that this is the area that's above the curve. But I wouldn't have even had to do that, would I? If I had just, all I need to know is where does the function pass through the x-axis, and then I could, just to play it safe, I could just take the absolute value of each increment of my integral, right? Absolute value of a positive number is still positive, so big deal. Hey, Michelle. No, I think she's isn't Katie at tennis or something?
Yeah.
Yeah, she's at Tennis State, I think. Yeah, bye.
I know.
Okay, see how that works? Where does the absolute value have to go? Does it have to go outside the integral, or could it go here? What happens if I take the absolute value of a function? Let's go to Desmos again. This is pretty interesting. What do you think it does if I just take a random function? You can tell I'm kind of addicted to Desmos.
So you're addicted?
I'm a little addicted to Desmos. I really am. I'll admit it.
It would like curve like twice last time.
Yeah. Okay. What's it going to do? I want you to think about that for a second before I do this.
Yeah, every you put in you get like
So let me just get a new blank graph. What was this function? X squared
Plus 2x minus 3.
plus 2x minus 3. Okay, there's my function. Okay, let's do g of x. And if I do absolute values around the whole thing, watch what it does. It just bounces everything off the x-axis. See how that works? Everything gets reflected. Everything that's below the x-axis gets bounced up above the x-axis. Okay? So, in this case, I want you to see, this is pretty cool. In this case, it wouldn't matter if I'm taking the absolute value of the entire area or the absolute value of the function, because, and it only works, you have to be careful about this, only because the limits of integration are going to be at the zeros of the function, it makes no difference, right? Because either way, if I take the absolute value of a negative area, I'm going to get a positive area. Or if I make the area positive first and then take its added up, I'm going to get the same value, right? But if the function, if I had different limits of integration, do you see that I would get different answers if I did that? Yes. Okay. So the way to do it most safely would be to just put the absolute values around the integrals. Okay? All right, so that's all it means when you want total area, is you're just going to break it up into intervals of area based on where the zeros of the function are, the real zeros of the function in the x-intercepts. Okay? All right. So I think I'm going to call her quits there, because that's kind of a logical breaking point. And then the next topic is totally different. I mean, it's related, but it's just a different thing. It's a bad time to start. Yep.
so one in real life you do it for a total area.
Okay, so a total area would be, here's an example. So we said that the area under a velocity time graph is displacement, right? Well, what if I didn't want to know displacement? Because here's my journey that we're going to look at kinematically. Say I start here, and I speed up, and I slow down, and I turn around and walk backwards, and I stop. So if I look at the area under my velocity time graph, the area under my velocity time graph is going to be 1 meter, because that's my displacement. What if I wanted to know the total distance I traveled?
You have to have both.
That'd be total area, wouldn't it? Right? Because I'm going to add up the area that I moved and my velocity is positive. I'm going to add this up. That's already positive displacement, right? But I'll take its absolute value and make it positive. And then the portion where my velocity function is negative, which is when I was walking backwards, that would show up as the velocities below the t-axis, right? So that's going to be negative area, but if I take its absolute value, I'm getting that negative displacement is going to show up as just a distance. And I could add those two things. Does that make sense? So there's an example of where you'd want to get a total area. Okay? Sometimes, some books call it net and gross area. Usually it's just total area and area, or net area.
Would they use that term more in economics?
I don't know. I've never really taken any calculus economics classes, but they might. They might.
It just seems like something that economics.
I could see it's possible. And you'll see different books and different teachers. Going from one teacher to another in college, they'll do things differently. But they'll pretty much tell you, you know. And you can figure it out. Just tomato, tomato. All right. Other questions?